Hello everybody. Let's continue our lecture series on optimal control guidance and estimation. We are in the third lecture of this constrained optimal control, which is going to be the last lecture in this constrained optimal control series. So far we have seen a little bit motivation of why we need, and especially a lot of practical problems demand that we explicitly account for that. Then we studied this control constrained optimal control problems in a generic framework in the Padhi's minimum principle framework actually. Then we use that in time optimal control of LTI system, essentially the minimum time problem sort of thing, and then demonstrated in detail about this double integral system. Okay. And fuel optimal control happens to be one of the topics in the book, but because of lack of time, I will rather leave it for self reading actually. You can read this topic from this chapter 7, these pages actually. Okay, it is not that difficult, it is very similar to time optimal control problem, just that there will be a singular arc in between, and then the function happens to be slightly different than just the signum function actually. But largely today in this particular lecture we will talk about energy optimal control, which is even more practically significant, especially in the framework of again linear time invariant systems. And then and towards end of this lecture we will also talk about state constrained optimal control, which is again quite critical actually in many applications. Alright, so just a little bit round up of summary of Padhi's minimum principle. The problem that we have been talking about is fairly generic. We have this nonlinear system dynamics, okay, and then we want to optimize this generic cost function, okay, and it also satisfies these proper boundary conditions. We are interested in finding some sort of a admissible time history of control variable from T0 to Tf. As compared to free optimal control or free optimization problems, so the only difference is control is constrained to lie on an admissible set actually, or in component wise it lies each of the component of control variable lies between some minimum and maximum value. Okay. So, in that setting we have already seen that the necessary conditions of optimality are very close to unconstrained case, but the only difference is the optimal control equation should satisfy this inequality. So, we can put it del s by del u equal to 0 and then try to solve a control actually. So, this inequality has to be carefully analyzed, and you have to actually see what u star, okay, minimizes this Hamiltonian function actually. Okay, so that analysis has to be carried out in a careful manner. And even if you see about kind of numerical procedures, this constraint has to be accounted for rather than solving the control from that del s by del e equal to 0. That's the only difference actually. But that's a huge difference. Just because of that difference, we end up with many different cases, different analysis, and all that actually. Alright, so that's the trick there. So now moving on to the energy optimal control of especially linear time invariant systems. The problem is natural in many cases. For example, if you have the control energy is typically it happens to be precious, and if you see electrical circuit, then the power consumption is I square R or V square by R, and if you consider this V as some sort of a control variable, then obviously we want to minimize that V square actually. Okay. And then if control in aerospace problems, control magnitude is restricted. Okay. So, control surface deflection should be as small as possible, especially to avoid saturation. As well as we typically want to minimize that to have sufficient margin for unexpected situations as well. For example, wind gust you have not taken into account, but suppose you want to cater for wind gust in while the plant is in operation, then it is better that we have some control margin left out. Okay, some bounds are there, so that we can still exercise that. Okay. And also as a small remark, rate of change of control, which happens to be a strong function of energy drainage from the power source, this is essentially some sort of a battery source in aerospace vehicle. That is small means it actually leads to some sort of smaller rates also. Okay. So, it is not really kind of obvious, it is not mathematically rigorous actually. In other words, somebody can also argue that okay, magnitude is small, okay, but the control can chatter within that actually. Okay, so the rate can be infinity actually. Okay, so those situations aside, typically when the control happens to be small, okay, it does I mean, what happens is if you bound it small, okay, and then this rate, I mean, it doesn't change that much actually. So rate happens to be small also, okay, because if you see this finite difference sort of things, rate is nothing but like xk plus 1 minus xk by delta t sort of thing. So if you fix delta t and the magnitudes are smaller, then the rate happens to be smaller as well actually. So usually it is smaller, even though mathematically it cannot claim it actually. Alright, so these are the small motivations why you want to talk about energy optimal control. So what's the problem here? We have a system dynamics in this form, linear form, x dot is x plus bu, initial condition is known, final time at t equal to tf, x of tf should go to 0, okay, especially when tf is free, okay. If tf is fixed, then it depends on where it wants to go, I mean how the system behaves to that and things like that actually, okay. But ultimately this x of tf has to be 0, okay, because otherwise what will happen is you have to account for that in the cost function actually, okay. Some quadratic terms will be there in the cost function. If that is not there, okay, what you are interested in is x of tf should be equal to 0 with this minimization actually. The control the cost, I mean cost functional to be minimized is a quadratic function of the control variable, okay. So tf is either fixed or free depending on the situation actually. Anyway, so control constraint, okay, typically it is in a normalized sense, it can be written something like that. Now magnitude of u is less than equal to 1, or component wise if you analyze, then each of the component uj is magnitude bound with 1. So control variable is normalized and the normalizing quantity is absorbed in the B matrix actually, okay. So that's what we have been talking about actually. Alright, so moving further, the energy optimal control system, formal statement happens to be like that. Energy optimal control system is to transfer the system dynamics from any initial state towards the origin at time tf, okay, either with the time tf can be either fixed or free, and at the same time it has to minimize this cost function with the control constraints in place actually. Okay. So that's the formal definition of a energy optimal control problem. Now how do we go ahead and solve it? We have this regular technique of applying necessary conditions of optimality. So Hamiltonian we define first, L plus lambda transpose F. So L happens to be half of U transpose RU, okay, and lambda transpose F happens to be AX plus VU, okay. So this is what is written, L half of U transpose RU plus lambda transpose AX plus VU, but I can expand that as lambda transpose AX plus lambda transpose VU. Now the state and co-state equations after that is like this, x dot is del S by del lambda. So again the same state equation appears with a optimal control function there, okay, and lambda dot is minus del H by del X, is equal to minus A transpose lambda, okay. Boundary conditions, x of t naught is x naught and lambda tf equal to 0, okay. Anyway, so these are certain details there actually. It doesn't matter to us so much about this formulation and all, very standard actually. And also let me put a small remark which I have been telling, that if you see the book, everywhere you will see a star notation, x star, lambda star, like that actually. Here we are purposefully taking out, because the inequality that you are interested in is control inequality only, okay. So what purposefully I put u star here and not any star anywhere else actually. But that doesn't mean that the state and lambda, I mean state and co-state are non-optimal. They are also optimal trajectories actually. Okay. All right. So this is the critical thing. Optimal control condition we want to analyze actually. Okay. So when you want to analyze that, Hamiltonian of x u star lambda should be less than equal to Hamiltonian of x lambda u basically, okay, or x u lambda, you can either way actually put that actually. Okay. Well, we have been following x u lambda, so probably you can put that as x u lambda everywhere actually, okay. This will be u, this will be lambda, and this will be, oh sorry, this, okay. Okay, It's just a notation sort of thing. Anyway, so this coming back to Hamiltonian definition. Okay, so this expression has to be put there, and one side is the optimal control function, one side is no any other control function actually. Okay. So this same expression with u star in the left hand side and the same expression without u star, just u in the right hand side. You can see one term cancels out, lambda transpose Ax and lambda transpose Ax cancels out. Okay, and what you are interested in is something like this actually. Okay, this inequality results in something like this. You have half of u transpose Ru with u star, and this expression with the lambda transpose B u star has to be less than equal to any other u basically. So, the equivalent of telling that this expression is nothing but minimization of this expression with this constraint in place actually. Okay. Now, here is a little bit piece of analysis. First, we define q star as something like R inverse B transpose lambda, and then this expression lambda transpose times B u star, which appears here, okay, can be actually analyze a little further. Tell okay, lambda transpose B u star is something like its own transpose, because ultimately it is a scalar quantity. So, you take its own transpose. So, you start transpose B transpose lambda, and then we introduce R times R inverse identity. R times R inverse is identity. So, we can introduce here, and then observe that this quantity is nothing but q star. Okay. So, then we note that lambda transpose B u star can be written as something like this also basically. Okay. So, hence this inequality what I see here, I can write it something like this. Okay. Instead of that expression, I will rather prefer to use that expression. Okay. There is reason for that actually. Okay. Now, after doing that, we can add this quantity to both sides. Okay. And then you can see that it essentially leads to some sort of a quadratic expression in the left hand side and quadratic expression in the right hand side. Okay. If you add this quantity here and this split it into two parts, half of that plus half of the other one, and one time you use this expression and one time you use that expression, and then combine in matrix vector form, then it turns out to be something like this. This is actually a quadratic term in the left hand side and quadratic term in the right hand side also. Okay. The difference is left hand side has used u star function and right hand side has simply u function actually. Okay. Alright. Now, we define for algebra simplicity this term, whatever term u plus q star sort of thing, okay, and w star is actually u star plus q star. Okay, w is u plus q star and w star is u star plus q star. Okay. So, what you see is u plus q star here, okay, and u star plus q star here. That is the reason we want to kind of simplify the algebra a little bit. Then the same expression what you see here, so same inequality can be expressed as something like this inequality now. Okay. Okay. And that is nothing but this minimization of this quantity with respect to this constraint basically. Okay. Alright. So, this is the simplified notation form. Now, here is a trick actually that it is a fact from convex optimization that this inequality is true if and only if this inequality is also true. Okay. There is a cursory proof in the book, it is not very rigorous, but some of you want to see, you can see that actually. Okay. So, if this inequality is true, okay, if and only if this inequality is also true, provided R is a positive definite matrix. Okay. So, R doesn't matter so much actually, okay, as long as R becomes R is a positive definite matrix actually. Okay. And utilizing this fact, okay, what you are telling is this minimization of this quantity subject to this constraint is equivalent to minimization of that quantity subject to this constraint. Okay. So, this is a critical observation actually. Okay. We will, without worrying so much on the proof part, we will continue our analysis assuming that this result is true. So, now we will end up with a case where you have to see that we have to minimize this quantity W transpose W with respect to this constraint actually. Okay. But this W transpose W with norm of norm of u or modulus of u being less than 1 is nothing but this is just a quadratic expression. Okay. So, this W transpose W is a vector, remember that. Okay, so because definition of W is like this, W is a vector. Okay, so W transpose W is nothing but summation of Wj squares. Okay, it's W1 square plus W2 square like that actually. Now, but Wj by definition, if I just go through that and put the definition there, then the Wj happens to be Uj plus Qj basically, right. This is the definition here. This is a vector, this is a vector. So, I can collect any component of W as component of that plus component of that basically. Okay, so that we write it here actually. Okay, Uj plus Qj stars whole square. Hence, the optimal control solution. Now, okay, here we are almost there actually. Now, what you are telling is we will end up with a case where you have to minimize this quantity, okay, subject to this, and this is nothing but that basically. Now, Uj depends strongly on Qj now, okay, and Qj happens to be this definition R inverse B transpose lambda, and if you recall your your knowledge about unconstrained optimal control, okay, then this expression pops up naturally, right. U star equal to minus R inverse B transpose lambda actually in that situation actually. Okay. So, anyway, so that is we will end up with some situation like this. Now, let us see what value of Uj I will select, so that this quantity becomes minimum quantity basically. Okay. And remember, this is a whole square term there actually. So, each of the term has to be minimum. Okay. This Uj plus Qj star whole square, that means U1 plus Q1 whole square plus U2 plus Q2 whole square like that actually. So, to minimize the entire quantity, we should have minimization of individual quantities actually. Okay. Now, if you analyze this, if you see this expression little carefully, all that it tells is, if Qj star is within the bound, okay, that means it is inside that, then all that is I can comfortably make it negative of that and make it 0 basically. This expression can, the minimum value is 0. So, if Qj star modulus is less than or equal to 1, then Uj can be comfortably written as minus Qj star, because that will satisfy the control bound actually. Okay. However, if Qj star is something like less than minus 1, let us say, okay, then whatever quantities I will have, I should have to have a minimum quantity there. Okay. So, if it is less than minus 1, then the best I can do is probably by putting plus 1 there, okay, that is the magnitude bound actually. Okay. So, even if it is something like minus 3, it is still going to be the summation will be minus 2. If it is minus 4, then its summation will be minus 3, that is the maximum we can do actually. So, we just leave it there. And similarly, if Qj star happens to be greater than plus 1, we just take it as minus 1 actually. Okay. So, that is the control formula that we will end up with. And also again as a remark, what we see here is even for a linear system, we will end up with a nonlinear controller actually. Okay, so that is how it is. Anyway, so now to kind of write it in a compact form, we notice that we can make take help of the saturation function, which is defined as something like this. If this input versus output, and saturation function is defined like this. If the magnitude is constrained within plus or and minus 1, then this is simply the same function. Output function is nothing but the input one. But if it is beyond that, then it is restricted to the bound value basically. Okay. So, if you take help of that, then Uj star happens to be the saturation function of negative Qj star, that is all actually. Okay. And combining all the components, so you can write it in vector form as something like this. Now, some comments or some observations rather. First of all, the energy optimal control law is described by saturation function, which is different from the signum function for time optimal control. That is the bang control sort of thing, is defined by signum function, and it is also like a dead zone function for fuel optimal control problems actually. Okay. Okay. Okay, this fuel optimal control problems. So, there we will end up with something like this actually. Okay. We have this this kind of a thing actually. Okay. Sorry, this is not slight mistake there. There we want to minimize the magnitude of control, and if you want to do that, there is some sort of a dead zone. Okay. Here it will be minus 1, okay. This value is minus 1, this value is plus 1, and this value is plus 1, and this value is minus 1. Like that actually, you will end up with this this dead zone sort of control actually. So, off bank control basically. That I leave it to for self reading sort of thing. So, you just read it in the book and see. So, now what happens here is in the singular arc between -1 to +1, control is really not defined. When not defined, people typically use 0 control. So, it's but still if you take theoretically if you take 0 control, then it becomes a defined control basically. So, the control is simply not defined. So, we switch off the control basically in a way basically. So, these are singular arc problems. But I mean if you talk about energy optimal control, it is a very well defined function. It is actually a continuous function. Okay. There is a -1 value, it starts varying to +1 and then goes there actually. So, this singular arc sort of thing does not happen actually. Now, U star is actually a continuous function of time. This kind of a function is certainly a continuous function. There are points at which the derivative is not defined, its derivative is continuous sort of thing, but then function sense it is continuous actually. Okay. And here is a critical observation. If the control is not constrained, then UN star is just that minus R inverse V transpose lambda, which is negative of Q star. And hence, if Q star this constraint is in place, Q star modulus is less than or equal to 1, then the constrained and unconstrained optimal control are typically the same thing actually. Okay. Right. So, all right. So, this is now another observation is the closed loop closed loop system is dictated by this function. X dot is Ax plus Bu. So, X star dot is Ax, but U happens to be something like this. So, saturation of minus R inverse V transpose lambda. So, we can put that and sometimes people write it as big letter, sometimes people write small letter like that actually. Okay. So, anyway, so that is X dot is Ax star minus saturation B times saturation function of that, okay. And then this system dynamics happens to be nonlinear actually. So, there is no closed form solution for that, you cannot write in exponential solution sort of thing. So, if you really want solution of that, then you have to do this numerical solution way actually. Okay. All right. So, this is what it is. Now, the critical observation here is this particular thing actually what we observe there. The constrained and unconstrained problem happens to be very close to each other basically. Okay. That means, if as long as it is within the bound, it behaves as if it is unconstrained problem actually. And only when it crosses that limit, then it is simply the same value, the bound value basically. And which is very intuitive. I mean, even if you don't know optimal control theory sort of thing, then this is how we implement basically. But naturally, it turns out to be the case when you talk about quadratic function of U being minimized actually. That means energy optimal control. This kind of a cost function actually. Okay. All right. So, that is an interesting observation. Now, to implement it, okay, we can have again two ways of implementing. One is an open loop implementation sense. So, that means you can assume something like lambda 0 and compute lambda t, because this expression is available with us. We can solve it once your lambda 0 is available, and then we can evaluate use a star, and then you can solve the system trajectory and monitor whether x of t f is 0 or not. If it is 0, fine, otherwise you come back and revise the lambda 0. But that is not very good, because there are infinite trials you have to do to get it there, and so hence this is not a very good procedure basically. And there should be a numerical procedure of how to adjust this lambda 0 in a proper direction and all that, like sorting method sort of thing, but we are not talking about that actually. Okay. So, what we are interested in, especially because it is a linear problem sort of thing, we are interested in having some sort of a closed loop or state feedback control actually. But anyway, if somebody wants to implement this way, this is how it is. You start with some guess value of lambda 0, then solve the system. This is A transpose, okay, and then get your lambda of t, and then get your Q star, pass it through the saturation function here, and then U star is available, but monitor X star how it develops, and at t equal to Tf is it 0 or not. If it is 0, then stop it, otherwise continue actually. Alright, but what you are interested in is closed loop implementation as a state feedback form. So, we are interested in some sort of a function, and we can still pass through that saturation function sort of thing, so that we will get optimal control. So, can we do that? And that is demonstrated again through a small example, because it depends on case to case actually. Alright, let us start that example. We have x dot is x plus u, where a is negative actually. So, it is a kind of a stable system. And we also know that for stable systems, typically the co-state dynamics is unstable. So, just remember that actually, we will need that actually. Okay, anyway, performance index is like this. So, if once you have u square dt, then r half, and you can put r equal to 2 actually. Okay. So, we have a is small a and b is 1, and q is not there of course, and r is 2 basically. Okay. And Tf is free and control is bound with absolute value of u being less than equal to 1. So, that is the standard problem actually. So, we have this Hamiltonian u square u square coming from this cost function L is u square plus lambda transpose f lambda times Ax plus lambda times u basically. Okay. Now, state equation x dot is del s by del lambda. So, Ax plus u star. But remember, A is negative quantity, again I emphasize that actually. Okay. So, co-state equation happens to be negative of del s by del x actually. Okay. So, that happens to be minus a lambda basically. Okay. So, that means minus a is positive, remember. So, lambda dot is now unstable equation actually. So, optimal control we already derived, that has to be a saturation function of minus R inverse B transpose, B is not there, B is 1. So, that is not written here. So, minus R inverse lambda, that means R is nothing but 2. So, R inverse is half actually. So, saturation function is nothing but negative of lambda by 2 basically, and saturation function defined this way again. So, U star happens to be plus 1 okay, if lambda by 2 is less than minus 1. Okay. It happens to be minus 1 if lambda by 2 is greater than plus 1, or it happens to be just negative of that value, okay, lambda minus lambda by 2 if this is within the bound actually. Okay. Alright. So, this may not be needed, we are not using lambda star anywhere actually. Okay. Alright. Anyway, so that's alright actually. Okay. So, we can also see that u star is equal to minus lambda by 2 can also be obtained from the unconstrained optimization, because once you have del s by del u equal to 0 and h is that del s by del u is 2u plus lambda equal to 0. So, it is u equal to minus lambda by 2 basically. Okay. So, that comment is still there basically. Alright. So, now coming to the analysis part of it, we want to have some closed loop or state feedback sort of solution actually. So, we go back to the co-state equation first, okay, and co-state equation solution is this way. Remember, A is negative, so minus A is positive actually. Okay. So, this is the solution. Okay. And also note that lambda 0 is 0, okay, is not admissible, because once lambda 0 is 0, okay, lambda t happens to be 0, it will remain at 0, and if lambda t happens to be 0, then u star happens to be 0, okay, all the time actually. And then x of t has to be just the homogeneous system, okay, and this homogeneous system will never reach to the origin in finite time actually. Okay. So, that is typically ruled out actually. Now, what you see is now this solution is still valid, lambda t equal to e to the power at into lambda of 0, but it has now 4 regions actually. We have to talk in something like lambda of 0 is 0 to 2, or it is greater than 2, or it is minus 2 to 0, or it is less than minus 2. The reason being, if it is if it lies between 0 to 2, okay. Okay, now I will come back to this slide. The solution nature happens to be something like this actually. Okay. If it starts between something there, then it remains there. If we start somewhere inside this bound, okay, minus 2 to plus 2, if it starts in a positive direction, it will sometime t a, it will cross that and go away. If it happens to start within this 0 to minus 2, so at some time t c, it will cross and go away actually. Okay. otherwise it will remain outside the bound actually. These are the 4 cases that we are talking actually. So, if it is there, why it is important? Because once this one crosses this bound of +2, then the saturation is in place actually, control saturation is in place. Within that it is not in place sort of thing actually. Okay. So, that is why we are talking about that. So, if it is that, u star is either that, either minus lambda by 2, or I mean you take this value, okay, minus lambda by 2, a minimum of that value actually. Okay. That means initially it will be like that and later it will stabilize at that. That is the meaning of this curly bracket actually. Okay. If it is always greater than 2, in that case lambda remains to be greater than 2 and the optimal solution happens to be -1, just the saturation value sort of thing. And similar analysis is there. If it is within this bound, okay, then at some time Tc, it will cross that. So, until that we apply minus lambda by 2 and then stay at +1 actually. Okay. And if it happens to be this side, then it is always saturated. So, it happens to be like that actually. Alright. So, this diagram I already explained actually. Now, coming back to the closed form solution, that is we are hunting out actually. How do you get that? So, here is a critical observation. We know that on optimal path Hamiltonian is a constant function, and if time Tf is free, Hamiltonian happens to be 0 actually, because I mean finally the Hamiltonian will go to 0. Now, Hamiltonian, if you just go back and see what is the expression for Hamiltonian, this is the expression for Hamiltonian. So, here we can substitute that and tell okay, this expression happens to be 0, and there I can solve for u as a function of x and lambda basically. Okay, or I can solve for x as a function of u and lambda, either way basically. Okay. So, this is solved for x as u and lambda. This constraint equation will be analyzed in detail basically. Now, we talk about a saturated region and unsaturated region separately basically. Okay. Now, if it happens to be saturated region at t equal to Ta, because this is, remember, this is Ta or Tc either way. So, what is that particular value of x at that particular time basically, that is we are interested in. So, at time t equal to Ta, lambda of Ta happens to be 2 and u star happens to be -1. So, we plug it back here, this expression, whatever expression you are having, u star is -1 and lambda happens to be 2. So, if you plug it that, you get 1 over 2 basically. Okay. And similarly, at t equal to Tc, lambda of Tc is -2, the other case actually what you are telling, and x of Tc we get a value now basically. In unsaturated region, u star is saturation function of this quantity. So, this happens to be negative lambda by 2. So, the Hamiltonian condition, again you go back and substitute that, u as a function of lambda, if you substitute that, we will end up with some quadratic expression in terms of lambda now. So, either lambda is 0 or lambda is 4x actually, but lambda 0 is ruled out, we just saw that little before actually. Okay. So, lambda 0 is not possible, it is not admissible. So, the only condition is lambda has to be equal to 4x and hence u star equal to minus lambda by 2 and there is nothing but minus 2x. So, summarizing all these, what you can see is if x is less than that, because instead of condition on lambda, this point of time we got a value for x also, and remember x is also kind of monotonic actually in a way. Okay. So, we got the value for x at this particular time or this particular time, that will kind of give us a feedback sort of formula, and which will tell, okay, I can summarize this something like a condition on x, not condition on lambda really. Okay. So, I will get if x is less than this one, remember a is negative again. So, this is a negative quantity. If x is less than that, but it is within that outside that basically, x is less than that, then I will have -1, x is greater than that quantity, then I will have +1. Okay. And otherwise, if it is within the bound, then I can operate that way actually. So, this is a state feedback formula basically. Yeah. Alright. So, this is what I wanted to talk in terms of this energy optimal control problem, and also it depends on case to case. If you have the nonlinear problem and or different sort of little more complex cost function and all, analysis has to be slightly different. Steps are laid out and you have to analyze in those steps actually basically. Okay. So, with that I think we will migrate to the state constraint problem now, before we wind up this series of lectures on constraint optimal control. So, state constraint problem has been studied from a variety of analysis tools essentially, and obviously everything is not possible for me to talk. So, I will confine into two elegant methods rather basically. So, first thing it talks about is penalty function method sort of thing. So, let us see what it is actually. So, suddenly you come out of this this Pontryagin principle and things like that. We are talking about state constraint PCUs here actually. So, the different tricks has to be applied here, unless it is a mixed state and control constraint. That has to be, I mean, that's again a topic in general actually. You can have problems with state constraints as well as control constraints. So, that's how it is, but here we are typically confined to primarily state constraint actually. Anyway, system dynamics, we will go back to nonlinear systems. System dynamics is nonlinear, performance index is generic, okay, and then the constraints are there, several constraints. In fact, 1, 2, 3 up to p constraints are there, okay, some sort of algebraic functions, okay, which has to be greater than equal to 0. That is a very generic way of looking at it. The only condition is p has to be less than equal to n. N is the dimension of the state actually. Okay. Otherwise, it may lead to some sort of over constraint problem and all that actually. So, we do not want to land up there actually. Anyway, so also there is another assumption which tells that the constraint functions, whatever functions we are talking here, okay, they have continuous first and second order partial derivatives. In other words, they are kind of smooth functions in all variables actually. Okay. How do you handle that? So, one idea is like this. So, all these constraint function I will collect whatever constraint functions are there, and I will write some sort of a state equation, additional auxiliary state equation x n plus 1 dot as some f n 1 x of t, where this f n plus 1 I will define it this way: g 1 square times h of g 1 plus g 2 square g 2 square times h of g 2, like that. And what are these h actually? H is nothing but something called unit Heaviside step function, defined as something like this. In other words, if the constraint is satisfied, then it is 0. If it is not satisfied, then it is 1. Then this is in place actually. Okay. If it is the constraint is satisfied, is not in place. Okay. If it is satisfied, is in place actually. But critical observation is, remember, this is either 0 or 1. So, it cannot be negative, each of the quantity. Okay. And each of these coefficients are also positive quantity. Okay. That means x n plus 1 dot is always guaranteed to be a positive quantity actually. Okay. I mean, greater than equal to 0, either it can be 0 or it can always guaranteed to be greater than 0 basically. But the interesting phenomenon is, this equation also demands a boundary condition. In fact, optimal control means we want 2 boundary conditions really for each state equation, and these 2 boundary conditions that we want to put purposefully is something like this: x n plus 1 at t0 is 0 and x n plus 1 tf is also 0. Remember, it starts with some value and it has to land up with that same value only, and both are zeros actually. Okay. Now, it is possible only when all this Heaviside function is 0 actually. That means, all state equations, I mean all constraints are satisfied. If one is not satisfied, then this is guaranteed to be positive, and even if it starts with some 0 value, it is going to go away actually. It is not going to come back to 0, okay, because at no point of time the derivative is really negative actually. Okay. So, that is the whole idea there. So, essentially what it does is, this formulation makes it some sort of an infeasible problem unless all constraints are satisfied. That is the critical observation actually. Alright. Now what is happening? We have an additional state equation, additional 2 boundary condition. That is all we have actually. Okay. So, we have this original problem, but in addition to that, we are imposing this state is, I mean, additional auxiliary state equation along with these 2 boundary condition, which forces the system to satisfy the constraints actually. Okay. So, now the rest of the things are plain algebra sort of thing. You have Hamiltonian, which is the L plus lambda transpose f, but we have one more equation. So, lambda n plus 1 times f n plus 1 actually. Okay. Right. This term lambda n plus 1 times f n plus 1 is coming in addition to what we already had. And state equation, obviously we have one more state equation. Okay. And co-state equation also, we have one more co-state equation. Okay. So, it will follow like that actually. But optimal control equation in general, when if you account for control constraints also on the way, then you have to talk about this way. Okay. This Hamiltonian has to be less than that, and you have to analyze there actually carefully. Again, I am not taking, I mean, these require numerical procedure to solve it also basically, and there are efficient ways of doing that as well. I am not going to lay out any numerical procedure in this lecture. I am just telling you the ideas here, okay, and rest of the things you can study in some reference literature, all sort of things actually. So, the whole idea here is you have this set of constraints and how to handle with that constraint. The constraints one way of doing that is putting these things and then carrying out rest of the things actually. An auxiliary state equation along with two boundary conditions, which is guaranteed to, I mean, if these are satisfied, then the problem is guaranteed to satisfy these constraints actually, whatever solution we get. Anyway, so this is what it is, rest of the things are algebra. Alright, so observation is we will end up with 2n, not only 2n, but 2n plus 2 differential equations, okay, one for x n dimensional state and one more n x n plus 1, one for lambda and n dimensional co-state, and then the corresponding n plus 1, this is a vector, this is a scalar actually. Okay. And also remember, when you do this algebra, this del h by del x and all that, now we should remember that these are also, I mean, this Hamiltonian contains this fn plus 1 and fn plus 1 contains these Heaviside functions. And Heaviside function is kind of a discontinuous function actually, okay. But having said that, it is discontinuous only at one point, that is x equal to 0, that too, okay. So, we can ignore that, but irrespective, I mean, other than that, it is actually a constant. The value of the constant is different, but actually it is a constant value, okay. So, do not get confused with that, the derivative has to be taken and all that. As far as these derivatives are concerned, del s by del x and all, these functions what you see here, these Heaviside functions can be treated as constants actually, okay. So, that is how it is actually, that is what is written here. Okay, Heaviside step functions are treated as constant functions in the co-state equation while evaluating this expression actually. And in fact, if you are interested, curious to see examples, you can see a typical small textbook example in the Naidu book actually. Yeah, that is that small example actually. Alright, so what are the boundary conditions that we are talking here? One is this boundary condition, which is already available. These two are imposed, these two boundary conditions are also available. But we are still not done, because we still need to have boundary conditions, some lambda f, Tf if it is free, like that actually. So, these boundary conditions can still be obtained from this general transversality condition, and suppose Tf is fixed, then this is 0, so this is gone, and Xf is free. So, I mean, if you consider that way, then it ultimately what happens is this has to be 0, that means lambda f is del phi by del x, which is known to us actually, okay. So, like that actually. So, boundary conditions have to be 2n plus 2. N is here, 2 are here, and n more will come from here, okay. And if Tf is also free, one more will come depending on the situation. Hamiltonian final time has to be equal to 0, and depending on situation like that actually. We have talked about that in early classes actually, when we talked about calculus of variations really. Anyway, so this is the summary of it, okay. The next idea, or rather the last idea that I want to talk in this class, is something called slack variable method. It's a different idea altogether, which is very elegant in my view actually. And in fact, it's also called Valentine's method. Okay, so it's because of this, because of F.A. Valentine, who first proposed this idea in some sort of static optimization sense actually. But anyway, so coming back, this is the same problem. Now, for more generality, we are having a penalty function also, the terminal penalty also here, okay. And then we have this constraint in place, and for simplicity we will take that as something like a scalar constraint. So, that is the reason why S is taken actually, but in general it can be vector also, it does not hurt actually. The formulation is without loss of generality. You will end up with more number of state equations actually, that is how it is. But assume that this is a scalar function, which is one constraint in place, but S is actually pth order, okay. That means, what do you mean by a function being pth order? The definition is like this: if you take p times derivative, p times time derivative, then u will appear explicitly, very close to what we know in dynamic inversion actually, those of you know that, okay. So, if I take pth time derivative of this function, okay, then the control appears explicitly in the pth order derivative, okay. And normally we have this either first or second order derivative with this control will start appearing. I mean most of the cases. We have this, let us say, a height constraint in a vehicle, then h dot is v sin gamma, and then if you take double dot of that, then gamma dot appears, and then control start appearing actually. Okay. So, like that actually, either that way actually, but in general it can be p third order actually. Now, how do you handle that? How do you analyze that actually? Now, idea is something very elegant. So, we actually introduce some sort of a slack variable alpha, okay, and then impose this constraint rather in equality sense. Okay. So, what happened to be an inequality here, we want to impose this alpha actually. But remember, this is also a slack variable, it is actually a slightly different in the sense of this KKT condition, this Karus-Kuhn-Tucker condition, the static optimization. That is where, I mean, if you recall that, at that point of time, we had the slack variable, but the slack variable computation was not done, and that was mainly for analysis only basically. Okay. It led to some elegant results, of course, basically. But here we are interested in computing these alphas actually. Okay. So, that is the critical difference actually. Okay. So, we have this inequality constraint, but we introducing this slack variable alpha, we make it equality constraint first, and depending on the problem we want to really compute alpha basically. Okay. Now, we differentiate this expression, start differentiating this expression. So, obviously, we have this s dot is written as s1, s double dot is written as s2 like that actually. Okay. So, then if you take first time derivative, because it is identically 0, all right hand side will be 0, and the first one will be s1 plus alpha times alpha 1, alpha times alpha dot rather is equal to 0. Then take second derivative, it will happen to be like that, you continue up to pth derivative actually. Okay. Now, here terms will involve alpha dot, alpha double dot, or alpha 1, alpha 2 like that actually up to alpha p. So, it will contain alpha 0th order derivative up to pth order derivative terms it will contain actually. Okay. Alright. So, now what actually? So, this is the definition of S1, what do you mean by S1 and what do you mean by alpha 1 like that actually. Okay. So, do not forget that it is ds by dt means we can compute this del s by del x, because s is a function of states basically. So, del s by del x into x dot, and like that you can continue actually. Similarly, alpha 1 by definition is d alpha by dt actually. Anyway, now coming back, what happens is we are assuming that this function is pth order, that means u appears explicitly. Okay, if I take pth order derivative here. So, from this pth order derivative constraint, this equation, okay, I can actually solve for the control in terms of other variables. Okay. Right, utilizing this expression, I can actually solve this control in terms of other variables actually, and that is where I symbolically we can write something like this, u equal to some function of x alpha and its derivatives. Okay. So, this is the critical observation really actually. Okay. Then what happens? I will go back and try to substitute my control in terms of that. Okay, remember x dot is f of x u and t of course. Okay. So, x of f of x u I can substitute in that way, because this is u, right. X dot is f of x u t basically. So, whatever u is there, u is that. Okay. So, I will substitute that as that. Then here I will treat this alpha p as control variable, new control variable. All other things are states actually. So, that means I have introduced new states alpha 1 things like that up to alpha p minus 1 actually. So, p more states are coming basically, and alpha p is treated as control variable. So, by first company, I mean this first canonical form and all that, if you see that first companion form and things like that, this one you can write it alpha dot equal to alpha 1 dot is alpha 2, all sort of things definition. And alpha p plus p, alpha p minus 1 dot is nothing but alpha p. Okay. And this alpha p happens to be a control variable basically. Okay. Now, what are the conditions? We also need initial conditions for that, remember that actually. Okay. So, alpha t equal to t0 is alpha t0, these are definitions alpha 1 t0 and things like that. So, we need values for that, then only the differential equations are complete actually. Now, how do you do that? This is also not that bad, because we know these expressions now, right. We started with that, this expressions actually. So, if you happen to, I mean, why can't we solve for alpha 1 like that actually? Okay, sequentially you can solve for that, and utilizing this expression we can first get alpha t naught at that. Remember x naught is available to us, that is the initial condition. So, it happens to be just a function of x naught only basically, okay. X naught and the constraint form, whatever is the constraint form actually, okay. I think this is, yeah. Okay. I think there is a small print mistake here. Let me correct that. Okay, this is like S basically. Okay, this is S1, this is S2, like that actually. Okay. So, from there you can see that actually. So, from the constraint expression and knowing the initial condition, we can know the initial conditions for T naught, I mean these guys also. The small ambiguity here, but typically I think if I will try for minus first and then go for plus actually, okay, because all other happens to be minus. So, to retain that same thing, but either way it is okay, because as far as constraint is concerned, both the values will satisfy that, okay, that is not a problem, okay. Alright, so that is how I will select actually. Okay. Alright, now alright, so what you are telling here is we have these additional state equations, and we want to know these initial conditions, and these initial conditions are available. That's the critical observation actually. So, it makes the problem complete really basically. Okay. So, now cost function is a matter of rewriting the cost function also. Instead of u, wherever u appears, I will substitute that and then treat it as something like a n plus p dimensional problem actually. Okay. In other words, if I define a state vector as x and all these p vectors alpha 1 up to alpha p minus 1, then I can rewrite the system dynamics as z dot is some other function f of z alpha p times t alpha p t, where alpha p is my control variable, and similarly the cost function can be written also like that. So, in this expanded state vector, in the high dimensional state vector, the problem gets redefined actually, where everything else is known to one. We know the differential equation, that set is, these are very simple differential equations anyway, and the associated initial conditions are also available to us, which happens to be derived from the same state equation, same kind of constraint equation function. Okay. So, it is elegant actually in that sense. So, from there onwards it is algebra. Okay. Then summary sense we can always talk like we redefine the state vector as something like this, larger dimensional state vector, control we treat that as alpha p, and then rest of the things we know how to do, define a Hamiltonian that way, and then the state equation happens to be this one in Z, and lambda dot happens to be like that, and things like that. Okay. Remember, part of this del phi by del z will happen to be simply zeros actually. Phi is a function of x, not alphas. So, when this alpha part comes there, that part will become zeros actually. The optimal control equation happens to be that way. Okay. So, and remember, we have actually, what is the trick here? By doing all these, okay, the constraints are accounted for, but absolutely, I mean this alpha p, when it comes to that, there is no constraint on that. It is actually unconstrained control problem. Okay, because this, right, I mean when you come to here, okay, there is no constraint equation, alpha p is still free basically that way. So, because alpha p is free, we can go ahead and straight away use that actually, del s by del alpha p equal to 0. Okay. So, this is, I think in my view is kind of elegant method, slug variable method, and if you will end up with some problem like that, you can give a try in this method actually, because it is not, see Heaviside, the other approach with using this Heaviside function and all is mathematically makes sense, but you may struggle numerically actually. Okay, it may not happen, then you may have to really struggle hard to tune the design in a good way. But I think the slug variable approach is kind of a natural way of handling the problem basically. You have this with inequality constraint, and you make it equality by introducing this function here right there, and then rest of the things are algebra, and it elegantly turns out that you can not only derive the state equations, but you can also get the associated initial conditions for that actually. Alright, so this is all about what I wanted to talk in this constraint optimal control series. and certainly I will encourage you to read many things, including thorough reading of this chapter 7 of this Naidu book. Actually, there are several elegant means kind of review papers also available, which you can see many things. But after knowing some of these things may be easier for you now actually. So I think with that I will stop this lecture. Thank you.